Load the GIS App 2 project from the last tutorial. Open the database editor if it isn't open. This time we'll import a shapefile of the road network. Open the road100k.met text file from the DVD Data folder. The Spatial Reference Information section indicates the data is in the same geographic NAD83 coordinate system we've been using. The Entity and Attribute Information section describes the one attribute we'll be using, Road Class. Launch the Import Wizard. Go to the Data folder on the DVD and open roads.shp. The wizard will correctly identify it as a shapefile. Go to the next window. The Load As window doesn't offer any options, so continue to the next window. Once again, we'll name the vector objects, this time Road. Go to the next window. The Coordinate System Editor pops up looking for guidance with the coordinate system. This shapefile continues our tradition in the geographic NAD83 system, so select it from the System drop-down list. Close the window. The Coordinate System Summary will update with the new system information. Continue to the next window. The Shape Options window opens to the attributes list, most of which we're not going to use. Deselect Assign DB names from an attribute field and select Conform to Terrain. Import the data. The first Database Fields window is looking for attributes. Select Road Class. The second Database Fields window is for assigning database layers. Select Road Class and import the data. After import is complete, select a road object in the database editor. The total object count will revise to 1504. Go to the Attributes page and confirm the road class import. The Layer page will have the road class value as a layer. Save the project as GIS App 3. Search the object list. Remove the number from the road search string in the input request box and search. VNS will find 301 road vectors. The last vector selected is on the 20 layer. Select the layer. Checking the metadata entity and attribute information, we see that 20 is a state highway. Go to the Database Editor Properties page. Change the render color to black and increase the line weight to 4. That takes care of 36 of the 301 roads, leaving us with 265. Return to the Layer page and select Road 202 on Layer 40, the neighborhood roads. Select the layer. That takes care of the remaining roads. Go back to Properties. Change the render color to 150 red, 150 green, and 150 blue. Save the project. Refresh the real-time views. The thick black line is the main road through the park, and the thin gray ones are side roads. Open the Fountain Flat Plan camera in the upper right view. Open the Fountain Flat Drive camera in the upper left view. Save the project and render a preview. If we want smooth curves in the roads, we're going to have to do something about those vectors. Activate the upper main road vector in the Fountain Flat Plan view and show points. We have two problems. First, there aren't enough points in the vector to show smooth curves at this scale. Second, the two main road segments visible in this view meet at an angle. Double-click the active vector to open its vector editor. Go to the Point Operations page. A fourfold increase worked with the Goose Lake vector, so let's try it here. Change number of points to 150 and change now. The real-time view will refresh with the new point count. Run a constrained render of the Fountain Flat Drive view. That looks good. Let's repeat the process with the other main road segment in view. Activate it in the Plan view. The vector editor will switch to the new vector. Change number of points to 20 and change now. Save the project. That takes care of the curves within the vectors, but what about the joint between them? Zoom into the Plan view twice with the plus key and activate the upper segment again. Click the second point up from the end. It will stay red and active while the other points fade to white. Change to Move Mode and click and drag the point southwest until the vector appears continuous with the lower segment. Select the next point north to activate it. Click and drag it southwest to smooth out the curve. Zoom out a notch and select the next point north. Drag it a little southwest. Select the next point north and repeat the process. Zoom out another notch and select the next point. Nudge it just a little to smooth the curve. Save the project and render a Fountain Flat Drive preview. Much better. Keep in mind that the addition of points to vectors is changing the data, though only through interpolation. Moving interpolated points is also changing the data. This usually isn't a problem because we're working at a scale below the original data resolution. Now that we've smoothed out the main road vector, let's pave it. Go to the Terrain Task Mode and add a Terraffector from the gallery. Load the two-lane highway. Accept the default Ecosystem Elevation Line Scaling option in the Load Terraffector window. Rename it Road Class 20. We'll use the Road Class 20 vectors to place the roads, so expand the Dynamic Link drop-down list and choose New Search Query. Turn to the Search Query Selected Filter page. Expand the Attribute Field drop-down list and select Road Class. Make the attribute equal to the value 20. Go to the General page and select Items Now to check the query. The database editor shows all 36 Road Class 20 roads selected, so the search query is set up correctly. While we have all the main road vectors selected, uncheck the Render box. Open the status log and clear its contents. Save the project. Switch out of Constrain Render mode and render a Fountain Flat Drive preview. Terraffector roads have added 43 megabytes to Terraffector memory requirements. Total effects memory now stands at 687 megabytes. The highway is more than a bit chunky. Slide down the lower Scene-at-a-Glance pane and open the terrain parameters. We're rendering at a maximum fractal depth of 0, which means we're rendering 2 polygons per 10-meter grid cell. VNS only renders one ground cover per polygon, which means the approximately 10 by 10 by 14 meter triangles can either have road or not. And that's what we're seeing. Increase the maximum fractal depth to 3. Save the project and render a preview. You'll notice that the increased fractal depth does not change the effect's memory. Close the log. The increased fractal depth took care of road detail, but also brought out the vertical displacement. The random roughness that vertical displacement adds to the terrain is important, but we'd like the flat areas with hydrothermal deposits to be noticeably smoother than surrounding areas. Go to the Land Cover Task Mode and open the Ground Effect Editor. Turn to the Material Gradient and Driver page. The hydrothermal deposits material is rendered on slopes between 0 and 5% of 90 degrees, or between slopes of 0 and 4.5 degrees. The transition to the next material, flat lower, is half blend. Let's see if we can create a similar transition with the vertical displacement. Go to the Terrain Task Mode. Change the vertical displacement to 3%. Create texture. In the Texture Editor, expand the Selected Element drop-down list and choose Dynamic Parameter. Expand the Parameter drop-down list and select Relative Elevation. Relative elevation is the measure of the elevation at a point relative to surrounding points. Convex upward terrain yields negative values, and concave terrain yields positive values. We want convex terrain to be flatter, so change the input high to 0. Where convex terrain has a relative elevation of -100 or lower, the texture will return a 0% value or no vertical displacement. Where flat or concave terrain has a relative elevation of 0 or higher, the texture will return a 100% value or 3% vertical displacement. Close the texture editor. Open another Fountain Flat Drive camera in the upper right view. Save the project and render a preview. Now let's add the side roads with the Road Class 40 attribute. Go to the Vector Task Mode. Expand the Search Queries category and clone the Road Class 20 query. Rename it Road Class 40. Turn to the selected filter page and change the attribute field equal to value to 40. Go back to the Search Query General page and select Items Now. 265 roads selected in the database editor confirms the query setup. Uncheck Render. Save the project. Go back to the Terrain Task Mode and add a Terraffector from the gallery. Load the worn 2-lane highway. Accept the default Ecosystem Elevation Line Scaling option in the Load Terraffector window. Rename the Terraffector Road Class 40. We'll place the worn road Terraffector with the search query we just created. Expand the Dynamic Link drop-down list and select Road Class 40. Edit Cross-Section Profile. The road surface section of the Terraffector uses the worn asphalt ecosystem. Edit the ecosystem to open its ecosystem editor. Go to the Ecosystem Editor Material and Foliage page, diffuse color, and edit texture. The texture editor shows the first single stripe texture element and its children in the middle thumbnail. We don't want the side roads to have broken stripes down the middle, so delete the first texture. We don't want the solid single stripe down the middle either, so delete that texture. We still have 2 single stripe elements left, but where are they? Increase the preview size to 10 meters. The first single stripe is the left white line, and the second one is the right line. That's the look we want, so close the editor and the profile. Open the status log and clear its contents. Save the project and render a preview. The new road Terraffectors have added 638 megabytes to the Terraffector memory, putting us over our maximum effect memory allocation. Open the component library. I'm increasing maximum effect memory to 2,000 megabytes, which is more than the 1.5 gigabytes of physical memory I have. Save the project and try another preview render. At some point, this will happen in most projects with lots of memory-consuming effects. You will increase maximum effects memory until you run out, and VNS gives you a memory allocation failure. Cancel out of the failure and render module windows. The last entry for Terraffector memory in the status log exceeds 1 gigabyte. It's time to start cutting project memory use. VNS required 195 megabytes of Terraffector memory to render the first road Terraffector, road class 20. Terraffector memory requirements increased to more than 1 gigabyte with the addition of the second road Terraffector, road class 40. Terraffectors seem like a good place to start reducing overall memory use. The more vector effects, the more memory. The higher the resolution of those effects, the more memory. One solution is to lower the resolution of the effects. Bring the Terraffector editor forward and change the resolution to 30 meters. This applies to all Terraffectors. Save the project and render the upper left view. The preview rendered with no memory error, and there's no apparent loss of road detail in this view. The status log shows a significant drop in Terraffector memory, only 185 megabytes. Open the fountain flat zoom camera in the upper right view. Save the project and render a preview. It looks like we have a Terraffector Priority issue here, but let's increase the rendered detail for a better look. Bring the terrain parameter editor forward and increase the maximum fractal depth to 5. Open the fountain flat zoom camera in the upper left view. Save the project and render a preview. Bring the Terraffector editor forward. The Terraffectors are set to overlap and have the same priority. This allows both of them to render if they overlap. If one road Terraffector had a higher priority, the other road wouldn't render at all if they overlapped. The two road Terraffectors overlap with the same priority, but they also have the same evaluation order. That means it's anybody's guess which one will render in the overlap area. If we want the main road, road class 20, to always render in the overlap area, it has to have the highest evaluation order. Increase its evaluation order to 2. Save the project and render the upper right preview. We can't do anything about the overlap along the main road. They are the same road class 20 Terraffector. We won't be rendering anywhere near this close, so it's not a problem. Anomalous spikes you may have should disappear when we lower the maximum fractal depth to the working value for this project. Bring the terrain parameter editor forward. Lower the maximum fractal depth back to 3. Save the project and render the upper right preview. Open the geyser basin camera in the upper left view. Switch back to real-time mode. Open the plan default camera in the upper right view. Switch it back to real-time mode. We can further reduce Terraffector and area Terraffector memory by freezing the effects into the terrain. The downside is that we lose all control over the Terraffected terrain. It's also not a good idea if you set shapefiles to re-import on project load and they change position. Let's see how it works. I suggest saving this part of the tutorial for the end of the day. It will take many hours to freeze all Terraffected DIMs. For this exercise, we'll just freeze the Lake Area Terraffector. Disable the Terraffector category in the scene at a glance. Open the Area Terraffector editor. Select Freeze All. An input request box pops up asking for a prefix for the frozen DIMs. The freeze operation will create new DIMs and disable the original ones. This makes it easy to revert back to your original DIMs. Let's stay with the default prefix. Confirm the operation. The status window on the animation toolbar will show DIM freezing progress. About 8 hours later, VNS completed the freeze process and asks if we'd like to disable all Terraffectors. The Lake Area Terraffector was the only one enabled and frozen, so click Yes. There are now 1,574 objects, which includes the 70 new FRZ YNP DIMs. The original YNP DIMs have been disabled. Select one of the FRZ DIMs and Object Search. Reduce the Input Request Search String to FRZ and search. Add the selected frozen DIMs to a new layer named Frozen DIMs. Enable the Terraffector category in the scene at a glance. Save the project and render a geyser basin preview. The Lake Area Terraffector has been disabled, so the log shows no area Terraffector memory use. Lake beds are now a permanent feature of the enabled frozen DIMs. Should we want to revert to the original DIMs and change the Lake Area Terraffector, we only need to disable the frozen DIMs, enable the original YNP-10M DIMs, and enable the Lake Area Terraffector.